We have a short introduction. So each one of you can tell your name and your affiliated institution. Yeah. So, introduction. Yeah, because section. It's not my name in Bangladesh. It's called in the Department of Engineering. শাশ্বত চক্রবর্তী মেকানিক্যাল ইঞ্জিনিয়ারিং Ladakh University chemical engineering. I'm using thesis for dating methods. Basics of medical students.
I'm Sunil Kumar Pandey. It's a scholar from Rajiv Gandhi Institute of Petroleum Technology. I'm department is chemical.
I think it's your I'm doing PhD from IT Masters in chemical.
I am Akhilesh Vasni. I am in my final year at in Agriculture Engineering.
When I'm doing from engineering and in PhD in chemical science.
My name is Salva Street. I'm going in my IT partner. Metal Engineering Department.
This must have been a from ICT and complicated. But
My education university was in technology.
I am Himadana. I am doing a better in competition committee. Anyone want to do it? What is it? Yeah, if you know their names, actually, yeah, please introduce. Your coordinator. My name is Rajiv Gandhi. I'm doing the same purpose. Okay. I'm Mangal. Except for that, I can do everything. Now we'll start. You got the revised version?
Yes, sir.
Today I have modified it.
Okay. Yeah. Okay. You're confusing. So,
I think
sir, it is also recording in the audio and screen record.
right. Okay, so I can start now. And listen के लिए यहाँ listen slide के लिए जी होगा ना okay fine. So again good morning. Okay, and again happy new year. Okay, so now I'll be teaching you the fundamental of the quantum. Okay, how from the quantum to we can go to the applied science basically. Okay, so that can be useful for different kind of process, maybe chemical, maybe mechanical, maybe civil, whatever it is bio. So I will start with the classical physics first. That why we need a quantum mechanics. Okay. So before that, this is my plan of lecture today. So we'll go briefly on introduction of quantum and how it has been originated. Okay. Then we'll go. I think those who are already doing this acoustic modeling, they know I think what is rectifier. I will be giving some brief about rectifier. Then this is also about then the main computational tool for nowadays all kind of modeling. Okay. And then I will give some those who are already using the computation, they know how the utility of function is done. But what is the fundamental of optimization? I will speak about that. Then thermodynamics, I think I know that thermodynamics is a ultimate. If your thermodynamics doesn't permit, you cannot go anything. Is it or not? So I will talk about how the thermodynamics can be done in quantum calculation. And then some one or because when the question in chemistry people, they always that structures to be figures. Not. So bond, the kind of thing, that kind of thing, all sort of things. They are always there in the slide in their mind. They will try to explain this bond is having a one bond, two bond, three bond, double bond, triple bond. You should say that. So that is why that natural bond orbital will did some in that process. Okay. And these two guys are basically they have agreed to collaborate that they will give you the hands-on session. Okay, so I'm lucky that they agreed to that. So Raghuval and Raymond, they will give the hands-on session. So now classical physics. Okay. So when we think about classical physics, first in our mind, what comes? Sequence of motion. Is it not? What is that? There is a P equal to force is equal to mass into acceleration. So we everything we think that everything is governed by that. That's the idea started by Galileo. And that has been given conceptual has been given by the Newton. Okay. So that is the thing. Law of motion. Okay. Now we'll see that whether that law of motion is valid or not. Later part we'll see that. So then three more laws by Newton. We are not going to do it here. So that will not help us in our to the future lectures. So now, the failure of classical physics. Okay, how classical physics? Can you identify what is this guy? what it is doing. This is result. What you are sending on pipeline. What it is giving. Okay, so what does it tell? The line is continuous or line is? Line is static or line is oil? What is it? Line is oil. So keep in mind. Okay, we'll talk later on that. Line is oil. Okay. So now I will talk about this four phenomena: black body radiation, photoelectric event, atomic line spectrum, and heat capacity of solid. For each part there is a classical physics. And we see that classical physics, whether it is able to capture all these four phenomena or not. Okay. Okay. So now black body radiation. How do you mean by black body? Anybody? Is it not? So it absorbs all kind of radiation. That is called black body. Is it not? So now when it is absorbing all kind of radiation. Okay, fine. So human are always prone to any phenomena, any effect. Human body is prone to put a law on that. Is it not? So anything is happening, we are always trying to find some correlation. And if that correlation is strong enough, we'll say the law and posterior, anything we used to say. So then black body radiation, Rayleigh and Jeans, they came up with the idea in June 19, this relation. Okay, the intensity equal to 2c by lambda to the power 4. And they plotted with versus wavelength and intensity. And when they are plotting and they are seeing that when they are going from the higher wavelength to lower wavelength, it is going increasing. Okay, fine. So this is their observation and their law. Now, when experiment was done, the experiment looks like this curve, red curve at high temperature, this curve. So something is wrong with this law. Okay. So what they have considered that this light, what is coming or what is emitting, it is a continuous. Okay. And you are telling it is oil. Okay. So they have considered it oil. Fine. So now this give some what I say idea to Planck. So he was thinking this guy has given the June 1900. And this guy, he came in October. You just hear how fast they are. How fast we are. Is it or not? So that guy gave in June, but he said that something is wrong here. He's trying very hard to come up with an idea. So he came up with the idea with one of the most fundamental constant that is called constant. You just imagine the value 6.626 into 10⁻34 joules second. Can you imagine the value? 34. You can measure. So, but he has got it just. I am not disregarding him. That he has got it just by trial and error method. Okay, but trial and error method was some scientific attitude, just not trial and error method. And then he came up with a revised law. And the revised law shows that he is beautifully capturing what is the low wavelength part. Okay, so this low wavelength, this guy is getting infinity. So that is why it is called ultraviolet catastrophe. If you this zone, this is basically ultraviolet zone, but this classical physics. Okay, so then this is the first idea of quantum mechanics originated. So what Planck told that energy which is coming in or out, they are not continuous. So that first quantization came to the Planck constant H and as well as this relation. So when if you plot, you can take it as homework. You can just make a Excel sheet. You can plot this equation because there is nothing great in this equation because you just make a column C constant, K is constant, T constant, and lambda you put this value, and you plot you will get this kind of thing, and you plot this equation also, then you get parameters. So you can make a homework. Okay, so the first quantization came, and then he proposed that energy comes it emits quantized. So basically, this N is a 0 to 1, 2, 3 up to N. Okay, and this H is a Planck constant. U is the frequency. So he came with the idea that H nu is nothing but the energy, and then we get the name quantum. So energy of particle is that is why the name we usually read in a textbook that quantum of particle is called energy particle is called quanta. Okay. Now here is his theory. Is you are happy? What do you think? You have developed a theory, which is a path breaking theory. So you should be happy. But he was not. You know, when he presented in the scientific, that time the scientific body was there. When he presented that people just laughing about that guy has done. So it is, but no one was taking it seriously. Right? So then, always in the history of science, always Einstein come in the rescue of the other people. Always you see here, I will come later on another point is there. So Einstein was thinking that this always for a long time it was there, that in the metal surface when the radiation is exposed on the metal surface, the particle of certain energy starts emitting. Okay. So then again, classical mechanics people always say that the kinetic energy that depends on the intensity of the radiation. This is the classical concept. Your energy is not quantized, it is a kinetic energy. Okay. So then, but experimentally it is seen that it follows this that when the electron is emitted, the kinetic energy depends on the frequency of the exposed radiation. Okay. So that is only possible if the particle having a quantized energy. Okay. So the Einstein came up with his own idea. Yeah. Last line is not coming, is it? One equation is other than telling product. That quantum energy you do U minus is not coming. No?
Yes.
Okay. No. Okay. So that electron, that one question I think you may quantum energy you do is H U minus work function. So that then he proposed that equation and he told that out of the light is not wave, it is particle. So then only you can explain this phenomenon. So Einstein supported the fact now that light will be anybody certificate. So Einstein is giving the certificate. So he's happy and then he realized that he has really done a great thing. Okay. So another thing. This is a anybody know what is the light spectrum? Anybody tell what is light spectrum? Since sodium and what is light color? That is the light spectrum. So if light is a continuous, so you will give it always all kind of spectrum you get, not a light spectrum. Okay, so but in generally we get different kind of spectrum. Okay, so this is possible only if in a electron which residing in the his home or orbit or household or will say in quantized is quantized or is a fixed energy level. So when electron jump from the highest to lower or low to high, it will always emit energy that will be quantized. Okay, so that is another thing, another proof that classical physics fails to explain of the light spectrum. Classical physics already tells that spectrum is continuous. Okay, so now after that, Rutherford came with the idea. Now you see that whenever a phenomena is happening, whenever a new phenomena is coming, people are always trying to capture that and try to put a theory. So this is the you just see the quantum, how quantum mechanics is evolving. Okay. So after that, in 1911, Rutherford proposed a model that Nicholas, I think people know that is a alphabetical experiment. Can anyone remember? So that experiment, how it is, it's in center there is a nucleus. It's surrounded by electrode. Okay. So he proposed that, but he could not come up with a sort of kind of equation. Okay, he proposed that kind of equation that's gives the idea to. So Bohr came in 1930 and he proposed his laws of hydrogen atom. That all electrons they are just revolving a path and that we call orbit or orbit. Okay. So and then this is the first law for the motion of an electron in the orbital comes with the idea of Bohr. So this is then we could explain that this is the emission of light and this is the absorption of light. So as I was telling you that if you need to start from initial final state to initial state or initial state to final state, you get a absorption light as well as emission light. And it's possible only if light is quantized. It is not a oil. Okay. Now, so how many people know this dual law? Anybody? Solid having a heat capacity 3 K. Have you heard? No. Nobody. Dual law. Okay, fine. So this is a one law. The very famous law. I think those solid state physics they are always have this law. So basically, it says that all solid have same precipitate. Is it possible? All solid will have a same precipitate. Not possible. If you are taking a precipitate at higher temperature. Okay. So now, okay, people are happy about that because at that time quantum mechanics was not there. So people were taking those values and using that. Okay. So, but now you see that there is always some bad guys. They cannot sit idle. Okay. They always try to find out that this guy has done something. Done something. Let us try to find out his drawback. Okay. So people are always there. When you are trying to find a drawback of a not you always get it. You still become up. Okay. So they are trying to do that. So what basically Petit told that basically he considered that it's a solids and made of a classical oscillator. Classical oscillator people have the idea of equivalence theorem. You know equivalence theorem? Really? So equivalence theorem is like that. It is a classical idea that if you are having a degree of freedom, each degree of freedom will contribute half kT. You know that. A lot of people know that. Okay. So now in case of solid, you are having a partial degree of freedom 3, you are having a partial degree of freedom in the momentum place. Okay. So you will get a 3 plus 3, 6 into half. So you will get a 3 Nk T. That is will be your energy. Now if you make the derivative of energy, d by dt, you will get 3 Nk. So Dulong has proposed that way. So what he has done, he has taken the classical oscillator. Okay. So now, again, Einstein came into the rescue. So clearly you see that this is a diamond. At high temperature, you see the value is quite close to 3. Okay, but when it comes down the temperature at low temperature, you see that it starts falling. Okay. So Einstein told that this is the failure is due to the consideration of classical oscillator. We should, instead of classical oscillator, go with a quantum oscillator. And that quantum oscillator means that each oscillator is having a frequency of omega 0. And if you do that, and if you can drive it, actually again that last question is coming, and you will get a one density of state, and from the density of state you can calculate, and you can get that value. And if you see that, from the final solution, and if you plot it versus specific heat versus temperature, you see that it is following the experimental trend very nicely. Not super important. So Einstein has proposed that what was the fault in the classical physics? He come with the if you accept if you take the quantum oscillator, you will get a correct measure for the physicality. So physicality is physicality depends on the vibration and how it follows that has given prescription is given by Einstein. So now Einstein is happy. Yeah? I say no, people are not happy with him. Not. So they will try to find out the some materials will be there where Einstein law. Okay. So one guy has come there. Now definition of the Einstein model. What is the definition of the Einstein model? You see. That was diamond. And this is silver. This is the experimental data. Okay. And this is the Einstein. This solid line. So you see that low temperature zone, resistance fails. It cannot capture the correct train of the precipitate. Okay. So now somebody has to restore Einstein. So who was there? That a device came into the picture. What device told? That Einstein, what? Yes, definitely has taken a correct oscillator in the sense that it is taken the quantum oscillator, not classical oscillator. So he can give the good trend with the experimental data. But what device is telling that okay, but the harmonic oscillator is not independent. Why? Suppose silver metal or now diamond metal. Is the atom isolated? No. So they are connected together. So each atom will feel the effect of the other atom. So it's a basically collective phenomena. So basically collective phenomena. Each atom will not have the same frequency. What I'm saying that all it is quantum oscillator and each oscillator having the same frequency. But what device it is not, they are coupled. So each atom will not have the same kind of frequency. There will be a distribution of frequency. So then he get the concept of frequency distribution in terms of wave. So he told that the atom it moves in the solid that basically generating a sound waves. Okay, that is basically sound wave, and this is a collective variable. So basically now the quantum oscillator will behave as a collective variable. So he took that correction and then finally he came with a if you see that part, this is the Einstein part. Okay, yellow one, this is the blue one. So then you get a correct model. So basically, my take is that classical physics cannot explain all the phenomena when you are in the quantum zone. How we are going to define the quantum zone will come later. Just now. Okay. So and only when quantum also laws proposed by the great people is also not always correct. Okay. But there are also some assumption or approximation they are taken, and those assumption or approximation you also have a chance to for something new. Okay, you think very deeply in their law. Okay. So now this is a great line. So Planck, Einstein, there are a group. So always there is a group of people, those who will follow there. And I always we are also having some thinking. We always have some kind of grouping, different kind of group people think differently. Einstein, Planck, they are in a particular way. There are some other people there in the way. So deep probably right, what is going on? So somebody is saying, so there is a dual group basically. So if there is a dual group, let us try to find out that there is a duality. There is a duality in the particle. So he came up with a very great idea that the particle lights behaves dual nature. Light have a dual nature or dual particle duality. That's Fermat law. Lambda equal to h by p. So now let us just I have given you that how it works. So I have given an example that is having a 1 gram marble and that is traveling at 10 centimeter per second. Okay. So now lambda is coming around 10 to the minus 30 angstrom. 10 to the minus 1 angstrom. You see your atom that is in the range of 0.24 angstrom, and your marble is 10 to the minus 20 angstrom. So it cannot give you the quantum nature. So that is why, though it is a partial character, but we don't have an instrument to measure it. We don't have the instrument to measure it. Okay, so that is why I'm able to capture the wave nature of the bigger particle or large particle. Okay, so once he has proposed his law, then some person, Davidson and German, they do the experiment and they come with that wave nature of the particle. They come up. So now it is proven totally. The light is composed of wave as well as particle. Okay. Now one interesting thing is that this guy is proposed this in 1924. Parallelly, he is looking on that. That he was just looking for an opportunity. That when some people will come and say that the particle will have some wave nature. Okay, so once that he told that to this particle duality that light is a wave nature, then he immediately come with the idea of quantum mechanics. Schrodinger in 1926. Yeah, Rahul? Oh yeah. Because of quantum mechanics. So this guy. These equation many people know. These are very simple equation. Only one is what is alphabet? One is alphabet, and another is the Greek letter. So alphabet, one Greek letter. Given another alphabet, another Greek letter. So very simple equation. But is it so simple? No simple. Why it is not so simple? Because this guy. side. Is it or not? This is simple. And not those that simple, but it's quite simple. You can define well defined. Hamiltonian you can well define. Is it not? You are having an atom, you can define his kinetic energy, you can define because you know his velocity, you can define. Electron, you can define. Their potential energy, you can define. But this guy is the undefined. Size, nobody knows what is psi. No, people know the psi is nothing but where the electron belongs. But what is its form? Nobody knows. Isn't it not? So there is a challenge. Okay, so now up to that, I am not going to now. Now I will just see since the topic of this slide is the quantum chemistry. Okay, so far we have discussed what? Physics. Is it or not? Classical physics and how classical physics fails and its failure originates given the birth of quantum mechanics. And now how chemistry people, not chemistry engineer, metallurgist or mechanical engineer, how they use this quantum mechanics in their domain. Okay. So here I will talk about that how chemistry people use that. You know already that physical, there is a topic called physical chemistry. So physical chemistry use this kind of thing. If those who have trained with the physical chemistry or those yourself are physical chemistry, you know, they are talking a lot about the molecular properties, is it not? This dipole moment, the international rotation, conformational transition state, chemical reaction. This is the domain of physical chemistry. So quantum mechanics, when you apply for explaining your physical chemistry, that is called quantum chemistry. Now, some organic chemistry, they will calculate the reaction intermediates, transition state. So they are using quantum chemistry. Okay. Then analytical chemistry, they are busy with that or the electropotential or spectra, different kind of spectra. So that is analytical chemistry. Then inorganic chemistry, they will the stability of the complex, gentle destruction, so many other things. So they are doing the quantum. Okay. So basically, what I mean to say here that people using quantum mechanics in explaining or interpretation of the chemistry phenomena or for the advancement of chemistry, that is basically quantum chemistry. Okay. So I will leave effort here, and then here I have not given the details because whatever these guys are doing, quantum chemistry, all are applicable to these guys also. So you can encompass all those things in this category, the chemical engineering and metallurgy. So now I call it this whole thing as a molecular engineering. Okay. So because basically I am a chemist, but I am working in engineering department. So I coined the name molecular engineering. Okay. So basically you are doing engineering in the atomic level. Okay. So you can change atom by atom. You can manipulate the atom. You can synthesize those molecules. You can use in the process of how you want to do. Is it or not? Well, you know that people that nowadays those who are doing this bone replacement. Then nowadays the bone is designed. You know. Bone is designed by atomic modeling that has been synthesized and that is used in the present. Is it or not? Those who are done biochemistry, docking, this is you are doing bioinformatics. Okay, so you can design a DNA also part by part. Okay, so and you can say come with a new molecule. Is it or not? So you can do anything. What I mean to say, as Feynman, I like that guy. He told that if you know the motion and position of an atom. If you know the position of motion, you can do anything. It may be a living thing, it may be a living thing. So that is called bottom-up approach. So using the bottom-up approach, you can design and you can do anything. Okay. So it does not see whether which subject, which discipline you work. Okay. So basically, in PRC, we are basically working in this solvent extraction, isotope those nodes, and then permission and storage of isotope. This work we do for the IEA or fusion reactor. This is for glass, membrane, adsorption. There are many other work, but I am basically working in this domain. Okay, so basically, what kind of software generally we use? There are many softwares, but I am using in my group. Basically, this is the software Ganes Thermomol 88. We are using for the isolated molecule. You know what is isolated molecule and condensate? You know, anybody? What is the isolated molecule? What is condensate? Or maybe what is the gaseous molecule? Or the condensate molecule? Give an example. That's water. If water is vapor, so molecules are far apart. Okay, so when the molecular interaction is not there, so you can say as isolated gases. or when the liquid is a condensed. So one molecule is attached to another molecule. There will be hydrogen bonding and some other thing. So that is a condensed phase. Okay, fine. So for those kind of calculation, you can do gaseous, tapamol, ADF, a lot of other thing is there. But when it is a solid or liquid, you can calculate as ATK quantum ratio. And basically another thing, I think later on, I think Professor Banerjee as well as they will talk about it. That is molecular dynamics simulation. Basically, the molecular dynamics simulation I will come later. What do you mean by force field? And this picture always I share with you in all my presentation. This guy is basically one Indian actually. So he is the first to give the liquid agar. First to simulate the liquid agar, sitting in the chemical lab using this machine. This is CDC in 1964. Yesterday I heard that somebody was Australian, they was Australian, that JNCSR is going to organize I think conference that is MD60, Malbar 60. To celebrate his contribution basically. Right? So that is a very great guy actually. So a lot of people are working on that now in the Malbar and Thomas Manuel group is working on many people working on that. Okay, so this is the tools I am using here. So basically lamps and bromance I am using. Now this is the few graphical graphics you may be knowing or you may be using other, a lot of other there. All are free software now. And now I will come to that. So we are stopped there at the east side. And then we discuss that how to construct sign. Since we know that return is not very difficult. Though it is also difficult. But it is going to sign. But sign is not going to. Okay. So basically, when we take three approximation to solve this equation. Okay. So one is the called Born-Oppenheimer approximation. So Born-Oppenheimer approximation people will know. Patusi, you will tell something what is Born-Oppenheimer approximation. You know? Can you tell? No. Everyone, can you tell what is Born-Oppenheimer approximation?
Basically, what about that? We use vulnerability. So there are two parts, encoding part and nuclear part. So if you consider both the parts, there are many proteins. They will like simplify the problem. So we don't have that complexity. So Bruno Primer came with two scientists. So it said that since the motion of electron is very fast with the metal nucleus. So what we can do is we can take the nucleus parameters, but it will be parameter variable. So variable is changing value and parameter you can fix. So based on the nuclear position, you solve the electronic motion. So basically you should solve the electric structure part. So you fix the nuclear parameter and you solve the electronic structure and you get a potential at the surface. So if you have seen that you get the wave mark. So at each nuclear position, you solve the electronic part. So that will be completed per make it easy.
Okay. So now basically from an approximate is that you know the psi is a consist of nucleus and electron. We don't know what is the form of psi. Scientists have given on the side that is square for it, but we don't know what is the form. So now the question is that how to approximate that psi so that we can come up with the trial psi which can represent psi. So then Bond come idea. They tell that electron that nucleus mass is compared to electron. How much? Yeah, 22,000 approximately. So now if you give the quantum energy expression, then half m d square. So now m is there, okay, and v also is there, and now the electron also is there, v is there. So the mass of nucleus is so heavy, motion, kinetic motion will be very slow compared to kinetic motion of the electron. So what I'm telling that when electron is moving, the nucleus is not feeling that electron. I will see it. Electron is readjusting itself such a way that as it is feeling that I am in there only. That center position is unelectron. So that is the concept of bond economy. But it is not always true. Some at the approximate lecture. So I will come later. But tomorrow I will come to that. Okay. Now this is a one approximation. Then independent particle approximation. This is a very important. That is the most important approximation in this construction of the site. So basically, it is very difficult to construct a house from many body or many electron. You cannot design. So until then, what scientists gave the idea that as if the electron is behaving as a independent particle. So they come to the idea that is started by Hartley first that you can construct a many-body wave function by taking a one-body wave function. Okay, I'm good with an approximation, but that approximation will take care by some other parameter. Then whatever the approximation I have taken, I can capture by some other thing. Okay, so now that is the thing, and that give to the approximation of LCMO. LCMO, what is this? This is called linear combination of atomic orbital. That gives to the molecular orbital. So if I having this three approximation, I can construct my site. I know my form of Hamiltonian. So if I have the trial site, which I can construct with little bit approximation, I can solve it. And my final aim is to get a wave function. If I get a function, I can use the Hamiltonian, I can get the energy of the system. So if I get a function, I can get the molecular geometry. If I do the molecular geometry, I can do lot of structural calculation. If I do the energy, I can do a lot of energetic calculation. Let's see how we do the calculation. Okay. How much time of first lecture I am having now? 11:30. Okay, fine, very good, nice. So now that bond association already I'm not going to take much time. Only that you see that to do the approximation. This is where your function of the nuclear coordinates are small r. Then you can make like this. That nuclear coordinates you can separate, and the electronic coordinates in presence of r. But now the electron has to be in presence of nucleus. Otherwise, it will be free electron. If it is a free electron, it is of no use for you. Okay, so that is why we are always keeping, but mostly we don't keep this r. It is implied that it is within some nuclear. Okay, but slowly you will see that I will not write in future. This r part I will not write. Okay, so but for you, I am just doing it. This is we have got this separable or separated wave function. Okay, so now our job is very easy. So thanks to these two guys. Okay, Born and Oppenheimer. You know Oppenheimer? But why is famous? Okay, so now this is a gentleman for Hartley and Fock. Okay, I'll come now. So this is the already I have shown you. Okay, so now if you want to get an energy, this is the expression. Okay, this is called variational equation. Variation equation to vary something. How do I vary something? Suppose you want to get something, some value with some prediction, with the some range. So suppose you are having a range, you can say that I have to go in this place. Okay, so you can go step by step. So you can divide the whole zone, and you can put a value, discrete value. Okay, suppose you are doing the integration a to b. Okay, in that integration a to b, so how we do the integration? We take small value, we are add up. There are some other time Simpson rules are there. So if you see that, we do that way. Okay, so now the variation, what do you do? Basically, this energy, if you minimize it, energy, to minimize it function, and for the true function, if your function is true, you will get the energy, and that energy must be minimized. So always, it is 1-to-1 collaboration. If you have got a minimum energy, in that minimum energy, definitely your function is true function. Or if you either way, if you have got a true function, in that if you got the energy, get the energy, that will must be minimum energy. Okay, fine. So now how we can partition this whole Hamiltonian like this? H then wave function already I told. I will just how to construct that, and then energy, and this I am defining like this. That basically this is the what I say this is kinetic energy of the electron, and this is the nuclear electron attraction. You will not see this all are one electron. There is no two electrons involved. Okay, so that is why it is called